We're pleased to welcome one of the leaders who's advancing software-defined vehicles and advanced technologies in vehicles. Today in the garage, the Senior Vice President of Electrical Hardware from Rivian. Let's go. Welcome to the garage. I'm John Heinlein, Chief Marketing Officer from Sonatus. In the garage, we bring together leaders across vehicle hardware and software, and today we have a special guest. We're pleased to welcome to the garage Vidya Rajagopalan, who's Vice President of Electrical Hardware at Rivian. Vidya, welcome to the garage.
Thank you. Thanks for having me, John.
It's our pleasure. And we were talking that you and I met many years ago. We figured it was around 15 years ago in 2009, where we worked together. I was at ARM at that time, and you were at Xilinx working on their Zinc, and you helped found and create their Zinc product line, which is really unique. I wonder if you can start by telling us a little bit about your background and maybe that product line where we first met.
Oh, that's great. So it's funny because when we both met, neither one of us was in the automotive business. I was at Xilinx. I had actually gone there to help their transition. Xilinx was known as an FPGA company. And they realized that for their growth, they really needed to expand their footprint. And I was brought in to help them build their first SoC product line. I helped launch the Zinc product, which interestingly, and I didn't realize at that point, probably what started my journey into automotive. One of the earliest applications was Zinc, was in the ADAS space for the front cameras. But I helped build the Zinc SoC line, which really was a big transition for Xilinx. It was an ARM-based system, and we worked with you on the ARM pieces, the IP. And it changed the whole story for Xilinx because it was really software programmable devices that could just boot up. We provided software, from Linux, and really helped our customers with a ready-made system on chip. And then really they could put their differentiated secret sauce in the FPGA.
Right. It's almost one of the kind of early precursors to software-defined vehicles in a way, bringing software into the hardware in new ways, I think.
That's right. That's right.
Now, after that, you went to Tesla for a while?
That's right. So, I had spent my entire career, I started my career building microprocessors at a company that most people probably don't know right now. It's called DEC. It was called DEC.
I worked at DEC years ago as well.
Oh, you did? Okay. Digital Equipment Corporation. And I worked there on the Alpha microprocessor, which was actually a pioneering microprocessor at that time. And I spent my really early part of my career doing microprocessors, systems, SoCs. And after Xilinx, where I had a really fun ride building the whole Zinc product, I was looking to do something different. And I wanted to do something that potentially, brought together some of the things that I was passionate about. And one was climate, and the other one was AI. And I saw Tesla as a place in the automotive industry, which was undergoing this remarkable disruption as a place where those two would come together. So that's what brought me into the automotive space, a passion for climate change, and really to address climate change.
That's great. I mean, Tesla did a lot of incredible, I would say, rule-breaking things, trying things in a new way that hadn't been done before. But now you're at Rivian, and you've been there several years. Tell us about your role there and your scope of responsibility.
That's right. So I'm at Rivian, and what I do here, I lead the electrical hardware team at Rivian. So electrical hardware is all things electrical, really. It's a loose name for that. It's down from the low voltage devices into more recently, I'm also running the high voltage side, the powertrain side of the electronics. That includes, the low voltage side includes all our controllers, ECUs, includes our wire harness, includes every really device that we have on it that's electronics, so displays, audio, the whole
nothing
thing.
Important.
Nothing important.
That's
well, it does make the car move, I guess.
It's incredible. And we're going to touch on almost every one of those aspects, I think, in today's conversation. We also like to get to know our guests at the beginning. You have to tell us a fun fact about you.
All right. So I have to fess up. I was not one of those people who, grew up dreaming about cars or played with cars or had car posters in my room. If you told me about 15 years ago that I'd be in the car business, I would have laughed outright. What brought me here was really my passion for both technology and really, as I said, addressing climate change. So people always assume when you're a car company that, you're a car nut. I got to fess up. That's not what got me here.
I think my situation is the same. I always like to match my guess, and I would say my background is exactly the same. I did microprocessors. I worked in hardware, computer architecture, many different things. I never expected to be applying my skills to automotive, but as you mentioned, one of the things, two things coming together in automotive. One is incredible technology integration that's happening in automotive, and then second is green sustainability. I think those are both excellent. It's one of the reasons I'm excited to be in this space as well. That's very exciting. I'm also especially excited to have you here because I'm such a huge fan of Rivian. I've been driving EVs now for, I think, about 12 years or something, and my current car lease is about to end, and I'm absolutely looking forward to getting a Rivian for my next car. So I'm very excited about that. But also the incredible engineering you guys have done. The R1 is a groundbreaking platform in and of itself, but then you've just announced, and probably we'll talk extensively today about the Generation 2 R1, which has incredible innovations from end to end, many of which you were involved in. You also announced, Rivian also announced the R2 and other models after that coming in, the year after next. So there's incredible innovation coming from Rivian, and I think it's you're such an emblematic of the innovation in the industry. So we're so happy to have you here. So as we think about the shift to SDVs, and we talk about many different aspects of the shift to SDVs here in the garage, but I think it's not one change that helps you get to an SDV. It's not like you flip one bit and all of a sudden now it's an SDV. It's an entire mindset shift of how you design the vehicle, how you design the hardware, how you design the software, how you design the networking. And one of the other things that's so impressive about what the work you're doing at Rivian is I think you're really showing how all of that can be done, especially with this recent change with R1 to R1 Gen 2. Your first generation R1 was super impressive, but the next generation has taken it to another level. So let's start maybe with the first of those aspects. And it's also kind of my personal favorite, which is ECU consolidation and integration. Because you can't have an SDV unless you're fundamentally sharing hardware. One of the defining factors of the opposite of SDV, of a hardware-defined vehicle, is one box does one job forever and ever. But that's not a software-defined vehicle. A software-defined vehicle has to have one box doing multiple jobs, sharing compute, isolating workloads across the thing. You've done incredible work in Rivian. Already, the Gen 1 R1 product was 17 ECUs, which is already much smaller than a typical vehicle, so already delivering on SDV. But in Gen 2, you just announced a few months ago, you've reduced that to only 7 major ECUs, plus a few small other ECUs, 7 ECUs. That's incredible. Tell us about that journey and some of your philosophy, how you got to that point.
Okay. So first of all, I'll say we'd be delighted to put you in one of our tri-motor or quad-motor vehicles. So whenever you're ready, reach out. Yes, so you're exactly right. It's not just about, how do you get a software-defined vehicle? It's not just about, saying I want to build one, but it starts really at the hardware. And it really starts, even before you build hardware, it starts at the system concept. So you start out from the very beginning, and that's, I think, what differentiates us. We start at the very beginning thinking about the entire vehicle as one electrical system. Right. And really, everybody says a car today is, computer and wheels. It's not one computer. It's a networked set of computers, right. Very diverse computers. In fact, if you look at the diversity in type of compute, you have high-performance compute, you have low, not that high performance, but real-time compute. You have really the diversity of compute that you don't have anywhere else, right. Or actuators, sensors, all
and
of that.
And safety critical systems too.
And safety critical and security critical.
That's
because
true.
You don't want anybody taking over. So it's a very complex system of many complex sensors, actuators, and compute types. And you have to look at it as such, as one big system, and we look at it from a clean sheet of paper approach, and which is what I think traditional OEMs struggle with, because when you buy a box from somebody else, what you're trying to do is, how do I put the boxes together? It's never in the optimal way, because you cannot put a bunch of, it's starting sort of bottom up,
right.
Which doesn't work. And so we look at it from a clean sheet of paper, look at all the tasks that we fundamentally are trying to do, figure out what kind of compute we need for those, and then we also look at, really, as we said, we talked about sensors and actuators. All of them have a natural point in the vehicle. And we look at, really, obviously, you want the computing, or even not the computing, the I/O to be very close to the actual sensor or actuator, because one of the big problems in vehicles, or the mass in vehicles, comes from the wiring. So we look at it as a really complex system that you optimize across many, many different vectors, right? So when we launched Rivian, our goal was to get a really compelling product out to our customers with the best technology out there. And the right trade-off for us at that point was a domain-based architecture, which was already one level of consolidation above what many other OEMs use. In a domain-based architecture, you have an ECU or control unit per group of or per category of functions. So for example, we had 17 ECUs, in-house ECUs, that controlled different function categories. For example, a body controller, which would control lighting, doors, wipers, things that attach to the body as it describes. Another controller for vehicle dynamics. And all of this, what it really enabled us to do was have dedicated software teams that worked on one control at a time. And it was a very efficient way to get a product out, and a compelling product out, not just any product. And as I said again, prior OEMs would have had many controllers doing the job of one of our domain controllers. So that's how we started. We came out, I think, and also I think even from the very get-go, and I should probably talk about that, our goal was always to be vertically integrated. Our intent was never to rely on hardware pieces from different suppliers. So that was very clear to us from the get-go.
Right. I think while you're taking processors, generally speaking, from outside, the system engineering and putting those into sort of computers, as people call them, you're doing a lot of that in-house.
That's right. Okay. We do that, yeah. So that was always the intent. We buy merchant silicon, but we integrate it in systems. That makes sense for us.
Yeah, I think it's a smart trade-off too, because you don't have to reinvent the wheel. There's a lot of great compute out there, but the system integration has got to be fit for purpose.
That's right, exactly. And even though it's fit for purpose, the thing I would say is we build it to scale. So we have the same ECUs that are in our Amazon vehicles, and we call them the EDVs, and they're the same ECUs that are in the R1S, R1T platform. So even though they're purpose-built, they're built to scale. And if you look at the EDV, which is a really big vehicle, and the R1, they're very different.
Right.
And we can really service both with one piece of hardware.
That's one of the benefits of software-defined vehicles, is that you can have the underlying foundation be the same, but you can customize whether it's accessories or peripherals or things like that could be
exactly. Yeah.
That's great. So, and you mentioned a domain-based architecture. Now, as you've gone to the second generation R1 platform that just came out, one of the things you've done is shift to a zonal architecture, or shift more fully towards the zonal architecture. Can you talk about that evolution and some of what that's enabled you to do? Because the wiring simplification is really compelling that you've been able to achieve.
That's right. So, we are, as I said earlier, our goal for Gen 1 is to get compelling product out quickly. And then our goal for Gen 2 was how do we optimize further? And the optimization, a lot of it has to do with improving manufacturing, reducing mass. It's not many, some of those, there are some optimizations that are obviously visible to customers, but a lot of it is actually not even visible to a customer. If you look at the R1 Gen 2, most people would not be able to tell the difference from an R1 Gen 1 unless you're really an expert. You can look at the difference in the cameras. But it was all very deliberate because we migrated from the domain-based architecture, zonal architecture, which allowed us to go from 17 ECUs to 7 ECUs. That, and why does that matter? It matters really from the point of view of it helped us reduce mass by 44 pounds. We reduced 1.6 miles of wiring, which is huge. And which for an EV, mass is really a big contributor to range, right? And then even having fewer wiring means fewer wires. You have to make connections in the factory. You need fewer people, or you can finish building a car sooner. So really these optimizations, many of them which are under the hood, have a lot to do with making Rivian be more efficient in the manufacturing process, use the battery pack more efficiently to get more range. So some of these are not really visible to other people, but they really make the vehicle much more efficient along the way. And we do have other optimizations for performance. For example, ADAS, we up-leveled our compute significantly. But the key about, why didn't we do a zonal architecture from the get-go? It's not like we didn't know we could build one.
Sure.
But there's a lot of software complexity in actually making that happen. So when we had the domain-based architecture before, it was the fastest way for us to get going. And that was important for a company our size to be able to do that. Because as I mentioned earlier, you had a team working on the thermal management module. You had another team. When you have a zonal architecture, you have all these different functions. each ECU now in a zonal architecture works on the physical space, at least the I/O portion of it, works on the physical space around it, which means, in the old days, I love to take the example of lighting. And a lighting controller would have controlled lighting all over the vehicle. So you'd have wires snaking all around the vehicle from one point. In a zonal controller, the zonal controller nearest the physical light that's close to it is the one that controls its I/O. But then that means to actually get that hardware simplicity, your software complexity went up. So now you have every zonal controller capable of handling lighting. And now you have multiple teams, working on different domains, now actually working on the same physical CPU, which means they have to learn to load share compute on the microprocessors. So there was a reason we didn't start from the get-go, but this really now enables us to really build a much stronger hardware foundation, which helps with cost, mass, a lot of other benefits, sustainability, all of that.
So this shift to zonal architectures, and we talk a lot about that on the podcast, it's really compelling for the reasons you mentioned. Now, you have 3 zones, front left, front right, and a rear zone. But you also have 4 major compute ECUs as well. One for infotainment and autonomy, sort of the navigation and the ADAS. One for battery management. One for access control. And then you've got a special one for the NFC around doors. So you still have some very high performance compute blocks, especially, for example, the one which does infotainment and autonomy, which has incredible performance. So this based on NVIDIA Orin processors, 2 NVIDIA Orin processors that deliver 250 trillion AI operations per second, which is incredible. Tell us about how you made the trade-off of those high-performance ECUs and that design in-house.
Absolutely. So I think, the zonal computers largely, pertain to sort of things like body functions, dynamics, thermal management, all
sensors, especially.
Really sensors, but I would say non-ADAS sensors because, you do have, so many different types of sensors.
True.
So we put all of that functionality, which is often real-time sensitive, in the zonal controllers, right? Not all of them are, but many are real-time sensitive because you've just responded in real time. And then we deliberately chose to keep the infotainment and ADAS separate. Because they're very distinct from what happens on the zonal controllers. The infotainment serves up all the experiences, that the driver or passenger may interact with. The telematics, connects the vehicle to the to the web or the internet. And then the ADAS is sort of another very high-powered system, which really takes all the information from the various sensors. We're a multimodal company. We use radar, cameras, IMU, GNSS, all of that. And then the ADAS obviously processes all the information and controls the actuators. So both infotainment and ADAS are very complex, and they really have high compute needs. The infotainment, because it has to serve up all the rich graphics, very different types of needs. So it was very clear to us zonals were one bundle, infotainment and telematics was one bundle, ADAS was one bundle, even though we physically put the ADAS and the infotainment in one box. And then vehicle access is just very unique. It's not as complicated an ECU as some of the, infotainment and ADAS, but really it needs to be located in such a way that it can sense people approaching. So it's actually, for that reason, a unit of its own, and similarly with the door handle ECU. And then we have a battery management system, which is really tied to the battery pack. And so very, we offer 2 types of batteries, and so therefore it really comes assembled with the battery, and so it's a discrete unit of its own.
Right. So it's a really, I think it's a really sensible, smart engineering trade-off, right? Where you've got the zones doing jobs physically close to things, real-time sensitive, wiring length is sensitive, but then these high-performance compute, generally speaking, higher-performance compute modules doing these other dedicated purpose things. Talking about vehicle networks, and earlier you said you were able to reduce 1.6 miles of wiring inside the vehicle, which is a staggering amount, and 44 pounds, I think you said, of wire. It simplifies the assembly. It simplifies the weight, of course, of the vehicle. You've also changed networking technologies because I believe the backbone of your vehicle is automotive Ethernet, but then within the zones talking to the sensors can still use existing protocols, things like CAN or LIN. Can you talk about some of the networking in your vehicles?
Sure. So first I should clarify the 44 pounds was not just from the wires, also from the ECU consolidation.
Of course, okay.
Because enclosure reduction itself gives you quite a bit. So yes, absolutely. We always actually, even our Gen 1 vehicle had automotive Ethernet. But I would say there is more automotive Ethernet in this generation. It was the backbone before, but it's a maybe stronger backbone this time around. And I think, Ethernet is remarkable for all the reasons, everybody knows and loves, the software stacks and the ease of communication, the bandwidth, obviously. But it still is not at the point today where it can be the communication medium everywhere. CAN and LIN really, are cheap, as simple. And the biggest thing they have going is their multi-drop capability of CAN. Whereas, with Ethernet, you really need to drop in switches everywhere. I know there's new technology with Ethernet, the 10BASE T1S, but, it's not there yet where we need it to be. So, yes, we use a hybrid approach. We use Ethernet as sort of a strong backbone for the bandwidth. We also use the time synchronization capabilities of Ethernet. But then when it comes down to communicating to, actuators, depends on the types of actuators and sensors. Some, for example, radar still works very well with Ethernet, but some sensors and actuators, we still largely use CAN and LIN locally, right? So that helps us keep the CAN and LIN more local to the zone areas and we do have CAN overall the vehicle, it's still there, but not as extensive as in previous generations. Okay.
And I assume then that must mean you're still sending some signals over Ethernet that are safety critical, right? Because you're leveraging time-sensitive networking for some safety signals over Ethernet?
Right. And I think it depends on how you classify safety, like things like airbags, communication, all of that is happening on dedicated, communication from sensors to the airbag control units is happening on specialized wires. Yes, we do definitely use, for example, I pick again, say radar input or something else would go down on Ethernet, yeah. But we have a very robust safety architecture. We look at it again, as I talked earlier, the advantages of having designing the entire vehicle architecture as a system. We look at in functional safety decomposition of the whole system at the vehicle level and make sure it's very robust.
Well, that's a perfect pivot. Let's talk about the software architecture more generally, because with this philosophy of doing a vertically integrated approach, you've had to think holistically. So tell us about some of the trade-offs and some of the things you've done there.
Absolutely. So I've talked a lot about the hardware because that's what my teams work on, but our software team has really done a remarkable job in this regard because we don't use any of the industry offerings such as AutoSAR. We really built, we look at it two ways. If you look at, we build our zonal controllers are built on a very robust in-house system that the teams have been developed and they have developed, and that's given us a remarkable amount of agility in terms of how quickly we're able to develop features, develop hardware, test, and bring it up. And it's really based on top of FreeRTOS, but we've really added a lot of layers to it and has been a very powerful tool for us. Similarly, on the autonomy side, while we use the processors from NVIDIA, we really believe strongly in building the application and the middleware layers and all of that. We obviously use the foundational elements from NVIDIA, but we've been building the software stack in that space too.
That's fantastic.
Right.
And I note that we mentioned earlier that you have this incredible 250 TOPS of performance. And we've talked with a number of other OEMs on the podcast about how sometimes it's challenging for them to justify headroom in their capability. And I heard a number of podcasts from your CEO talked really articulately about your philosophy of wanting to make sure you can plan for the future and expand the capabilities. Tell us about that decision you made to bake in some headroom.
Absolutely. And I think in that particular space, from Gen 1 to Gen 2, as I said, a lot of the changes were more for our cost, manufacturing, ease, and all of that. But in the ADAS space, it's very clear. We put in a lot of headroom. We're 10x the compute capability for previous generation. We have more sensing. Our camera is 8 megapixels. So we really, from sensing to compute, we up-leveled our ADAS significantly, and we definitely put in headroom because I think the ADAS software journey has just started for us, and there's really long way. We find already that our teams are very capable of capturing all those tops. And, with both our prior background in microprocessor designs, that software will use up all the compute and the memory you provide. But we're already seeing, if you start using all of the next generation transformer-based models, all the sophisticated models, you need those tops and more, frankly.
Yeah. And in autonomy and ADAS and autonomy, depending on where you like to be on that perspective, the mindset's still evolving, the regulations are still evolving. And so I think you're beginning, what I've heard is you're beginning with a modest level of, incredible capabilities, but you're also leaving the future as people's appetite increases and regulation increases to do more and more.
That's right. And I think, what I would say is you're exactly right. First of all, when people talk about autonomy, our team is called autonomy, but it's a continuum. It's not a level 4. We don't really go into that discussion. It's really, I think, all the way, all of autonomy, that whole journey made possible all the safety features that are in vehicles today, like, automatic emergency braking. So there, it's really that whole umbrella of all the safety features, as well as the self-driving capabilities. And what we did consciously is really keep headroom, because the whole philosophy's improvements over with OTA, enabling more features with OTA. And ADAS is far more sophisticated, or autonomy or ADAS, because to actually add more and more features over time, there's a complex AI loop, which involves data gathering, training, and that takes time. And so we know we're on that journey, but we know it takes time. And so it's important to have that headroom for that exact reason. Right?
Yeah, one of your things you talked about recently was the fact that you have a very tight feedback. You just mentioned feedback loop, being able to take driving experiences from your vehicles, anonymized, of course, take them to the cloud to learn,
right,
so that your vehicles can get smarter and you can see a situation, the vehicle handled it this way, but we should have handled it this way. And tomorrow and the next day, the vehicle gets better.
That's right.
And that cycle of learning is important. We've talked about that at Sonatus. We've shown a demonstration how you can use our technology to do a similar thing, to be able to get feedback to the ADAS system saying, hey, there was this very strange situation. Why did that happen? Or can we capture situations like that to fix the problem in the future? I think it's an important feedback loop you mentioned.
Absolutely. I think that's really key. And we actually do that everywhere, not just ADAS, right? We have some headroom in all our systems, and we're always learning. And really, that's another power of software-defined vehicles, is the power of OTA, right? And we add features continually and expect to over the lifetime of the vehicle, and our users start to look forward to it. It's just like when you get your new feature in iOS, right?
You mentioning OTA, it's perfect, because I was hoping we would talk about that a little. Your vehicles already today, you've done over 30 OTA updates since you launched your vehicles, over 500 new features you've handed out to your customers. Of course, then not to mention improvements in the way features already work. Tell us about your philosophy of OTA. We spoke about that the other day.
Right. And so for us, OTA is key, right? OTA is key because that multiple reasons. That despite the best of efforts, bugs happen. And you don't really want to have to go, and if you find out later on that you had some buggy software, or sometimes even buggy hardware, which you can work around through software. But if you had buggy software, you don't really want to have to have the customer bring their vehicle into service. It's inconvenient for them. It's actually a big overhead for us as manufacturers. So for us, OTA is almost a requirement for every piece of hardware that sits in the vehicle that runs any software. And that's our philosophy. Very, very, very few. I would say the exceptions are very minor. It has to be something really trivial and dumb that you don't really care about.
Yeah, you said you had a philosophy, it either has to be dumb or upgradable. Is that what your philosophy?
Exactly.
So a simple sensor that it's fine, we know what the sensor is going to do.
Right.
Everything else should be upgradable over time.
That's right. It has to be really simple. Maybe a little light that has something we might be okay with, where it's hard for it to go wrong.
And so that fundamentally means you're committed in a major way to being able to do OTAs across the vehicle.
Exactly.
Because I think a lot of companies, when they talk about OTA, they're going to give some new feature in the infotainment or something, of course, ADAS perhaps. But most companies, I think, are not committed to pushing it throughout the vehicles to the same extent. You're fully committed.
Absolutely, fully committed. And we take that very seriously. And when we do part selection in the beginning, that's a very key criteria. Obviously, the ECUs we develop in-house, they're really built for OTA. We design them. But even when we procure vendor parts, and we do have some vendor parts, we make sure that we have a clear handshake with them and a plan for OTA. And, we down to requirements and bootloaders, security, safety, all of that, right? And like we said, there are a multitude of reasons. One is to just be able to offer features down the road. The other one is to fix software bugs. And the other one, and very rare, is really work around that, what may be a hardware issue.
We've touched on so many interesting topics so far. I wonder if you could finish by telling us a little bit about the new R2 model, which was announced recently. Everyone is very excited about it. It's a little bit further out in time, 2026, first SOP. Tell us a little bit about R2.
That's right. So R2 is part of what we call our mid-size platform that actually includes R2 and R3. And we revealed both of them earlier this year. The R2 will launch first in 2026. So in terms of the electrical architecture, all the work we did in R1 Gen 2 was sort of a precursor. It was very deliberate. It was not just done for R1 Gen 2, but it was meant to be a platform that we'd pick up for R2. So, all the work we did in establishing a zonal architecture will carry that forward. Not exactly the same ECUs, but modified ECUs. That concept of the zonal architecture will go forward into R2. We obviously will do, a big refresh of the infotainment platform because you expect by that time the demands of, infotainment to go up. We have a few other tricks up our sleeve. ADAS and autonomy. A lot of the focus really, the sensors, we did a huge up-leveling of the sensors, from like one megapixel cameras to 8. We think that's actually pretty robust and will stay there. And by doing that, we can actually leverage all the data and the training we would have done from the R1 Gen 2 platform and carry that forward into R2. So it really was a very deliberate step we did earlier on so that we'll have a long, stable platform on the sensor front. And then a lot of the innovation in terms of not innovation, we will innovate everywhere, but the integration effort that we did, going from 17 to 7 ECUs on the low voltage side, we're going to be doing that actually on the high voltage side. So we're actually going to look at being more clever in terms of how we integrate all our power electronics. So we're continuously, working on improving things.
So from an engineering side, really sensible trade-offs of R1 Gen 1, R1 Gen 2 evolution, and that same learning and can transfer a lot of that to R2, but some nice, as you say, tricks up your sleeve and some great innovations.
And then really the focus on, Gen 2 for us is a lower, not Gen 2, R2, yeah. It's a lower price point. So obviously we're looking at our zonal architecture, our wiring, all of that and saying, how do I achieve a lower price point, right? With that. And so there's a lot of work and optimization around that, but we get to work on a more stable zonal platform at this point. So,
well, it's a very exciting times ahead. Where I'm from an engineering side and from a driver and a car lover side. It's exciting to see all the work you're doing, and I'm so proud to see you as a friend of mine that all the incredible contributions you've made to this great company and to this great platform. So, thank you for joining us.
Well, thank you for having me here. So it's been a pleasure, and it's remarkable. When you leave companies, you say you never know when our paths will cross, and I never expected to run into you. With both of us doing the similar things. With both of us being in the vehicle company.
That's right. Yes. Thank you so much.
Thank you. My pleasure. All right.
If you like what you're seeing on The Garage, we hope you'll like and subscribe to see more episodes like this. Thank you for joining us, and we look forward to seeing you again very soon.